Hey everyone, in this video we're going to be solving question 7 from the discussion 3B worksheet from Physics 103. So this question is dealing with the Atwood machine, which is a device composed of two masses connected by a string over a pulley. So we can assume that this string doesn't stretch and it's always taut, which means that it's always pulled tight. Now because there's no stretching and it is taut, we can assume that when this pulley rotates either clockwise or counterclockwise, M1 is going to move up at the same speed M2 moves downward. Or if it moves counterclockwise, the opposite would be true. So we want to derive an expression for the motion of M1. And what that means is essentially we want an expression that identifies the acceleration of M1. How fast will it accelerate, either upward or downward? However, since we said M2 will move at the same rate of M1, we basically just want the acceleration of the system. So we're going to be able to solve for acceleration by incorporating Newton's second law, specifically this part of it here. But before we do that, I wanted to redraw this so we can see how we're designating the direction of our forces. So imagine I took M1 and I flipped it up over M2, but I kept the string flush with the pulley. So here's my string, and here are my masses. Here's my M1, here's my M2. Now these forces work in tandem, so any forces that help the pulley rotate counterclockwise clockwise are going to be paired, and forces that help it rotate counterclockwise are going to be paired. So let's start with clockwise. We would say that the force of M1, let me change my notation really quick. M2 is on the bottom, and if we flipped M1 up and over, that's on top in this linear drawing. So let's do the counterclockwise, or the clockwise forces, which we'll designate as in the positive direction. Counterclockwise we'll designate in the negative direction. So the forces that help it move clockwise are pointed this way. So from M2, this is that bottom or downward force, which is the weight force. Going back to our equation, weight force is equal to the mass times gravity. So that's the mass, just M2 multiplied by gravity. Now for M1, this is actually the force that's up, which is shown here. For M1, this is the tension in the string that's pulling M1 upward. So we have now designated those two forces as positive, helping move it clockwise. Now let's talk about counterclockwise forces. For M2, it's going to be in this direction as it will be for M1. So in M1, the negative force is actually the weight force, which is M1 times gravity. The negative force for M2 is the same tension in the string. So let's go ahead and fill those in. M1G. Now I could change my notation or my coordinate system so clockwise is negative, counterclockwise is positive, and then I'd just flip all the symbols and you'll still get the right answer when it's all said and done. So now that we've identified our forces that act on both M1 and M2, let's look to Newton's second law. And what I want to do is take the law, which is the sum of all the external forces equals mass times acceleration, and form two tailored expressions, one for M1 and one for M2, that kind of summarize all the movement. So for this part of the equation, we are summing all of the external forces acting on the object. So for M1, the only external forces we have are the weight and the tension. So now we have to take into account the sign of the weight and the tension. So looking at our linear picture for M1, we have our positive force, which is tension, plus the negative force, so just minus M1G, and that's equal to the mass, M1, times acceleration. The other tailored equation for M2 is just going to be the tension and the weight as well, but now they're flipped because here the weight is positive M2G plus the negative tension, or just minus tension, equals the mass of the system, M2, times the acceleration. So now we have our two custom equations, and what we can do is identify similar variables in both of these equations. Tension is the same, and also acceleration is the same. We said that's so because we can assume the string is taut and it doesn't stretch. And we eventually want to solve for acceleration, which means we need to preserve that variable and eliminate tension. How can we do that? By solving or rearranging both of these equations in terms of tension. And then we can proceed to find acceleration. So let's do that really quick. In this equation, summarizing M1, tension equals M1A plus M1G. In the blue equation, summarizing M2, tension is equal to M2G minus M2A. So now that we have both equations solved for T, we can set this part equal to this part, which is the same thing as setting T equal to T. So let's do that. M1A plus M1G is now equal to M2G minus M2A. I'm going to rearrange and try to isolate acceleration. So I'm going to bring like terms on the same side. So I have acceleration here and acceleration here. So I'm going to bring that term over. And I have gravity here and gravity here. So I'm going to bring that term over there. So M1A plus M2A is equal to M2G minus M1G. Now I'm going to extract acceleration from the left side of the equation, which puts M1 plus M2 in parentheses, and also do the same for gravity, which puts M2 minus M1 on this side. So now one more sweep, putting M1 over there, I have acceleration equals gravity multiplied by M2 minus M1 all over M1 plus M2. So now we've actually come up with our function that projects and models the motion of a system given the masses of M1 and M2.